All right. It's a rainy day out here on this side of physics land, right? So hopefully we don't lose any connection here. All right. Are you hearing me? Do you hear me now? Good. Do you hear me now? Good. All right. So today we're talking about friction. My name is John Frensley. I work at Prosper High School, north of Dallas. This is C Mechanics. And so not everybody really loves friction. I know that when I see it on a problem, it kind of, makes me cringe, but it's something we got to deal with. It's a part of our lives, so that's just life, right? So here's a warm up for y'all. Okay, so this is going to be a little kind of quick warm up here. I'm only going to give you 2 minutes on it. You got a 10-kilogram box. And by the way, can we set a couple of ground rules? Please let G equal 10 this entire time, like unless I say otherwise. Just so much easier to do math with G equals 10. On the AP exam, they'll take 10 or 9.8. So just whichever one you prefer to use. And just this is a programming note. This whole set of slides is going to be good for Physics 1 as well. We're not doing any calculus this time, but the next time we're together, which is going to be on Monday, we're going to do a bunch of calculus. So the next time is not going to be P1 friends. Now I'm doing that on Tuesday. Miss Jen's Fold is doing something on Monday, and I'll have to check the schedule. That might be P1 friendly, but on Tuesday it's going to be air resistance forces with me. And that ain't going to be for P1. I'm just going to tell you that right now. Okay, but this is going to be P1 and C mechanics. This is all good for you. 10-kilogram box, use G equals 10 for me. It's on a flat surface. You've got a coefficient of friction 0.6, static friction, coefficient kinetic friction 0.4. We're going to apply a force F to the box. There's two parts to this problem. Part A has an F force and part B has a different F force, right? So what is the box's acceleration in each case? Part A, we're going to apply a 50 Newton force to this box. Part B, we're going to apply a 70 Newton force to this box. So each one's going to give a different amount of acceleration here, right? So I'm going to give you 2 minutes to crunch this over. On your mark and set, go. All right, that's the end of that. Now we will get to see what the answers to these are a little bit later on, but let's just take a little look at what we're going to be looking at today. All right, we're going to talk about friction, static and kinetic friction. I know it just gets better every time. We're going to look at Newton's first, second laws. We're going to apply them to situations where the objects move horizontally and they're subject to friction. Then we're going to look at friction when the forces are not nice and parallel or perpendicular to the motion. We're thinking about inclines and pulling things at an angle with the rope and all that good stuff. Okay, here's what you need to know about friction. So you need to know friction opposes sliding. Sliding, not motion, sliding. So so what do you mean? Are those not the same thing? Not quite, okay? Just because something is moving does not mean that there's necessarily friction on it, or because something is not moving, there might still be friction on it. It's all about sliding. So when you push on the brakes in your car, friction slows your car down. So if I am, let's say, driving to the right, then when I push the brakes, the friction force acts to the left in order to slow me down. However, this is key. When you push the gas pedal in your car, so if I'm driving to the right and I push the gas, then friction is actually acting in the same direction that I'm driving. This is a big misconception. Students say, hey, if you're going to the right, friction must be to the left. But wait, sometimes friction helps you go. In this case, friction helps me go so that my wheels don't peel out on the pavement, right? Now, when friction helps you go, you might be used to calling it traction, but traction and friction are actually the same physical effect. It's the same bonding between the molecules kind of thing. So you call it traction when it helps you go. You call it friction when you hold it back, but it's really friction either way. So it's important to know friction sometimes helps you go and sometimes holds you back, right? So got two types of friction. So static friction. Static friction is going to act when the objects are trying to slide but are not yet in the process of sliding. The goal of static friction is to prevent sliding from even taking place. Whereas on the other hand, kinetic friction, that's what happens when you're already in the process of sliding. So the goal of kinetic friction is to make the sliding quit happening. So the sliding hasn't started yet, but it's trying. Static friction gets hired for the job. The sliding is already happening. Then it's time to get kinetic friction and to make the sliding quit, right? So I always thought of static friction as like preventative medicine. What do you think preventative medicine is about? Well, it says it in its name. It's about preventing you from getting sick. So if you go get a vaccine, then that's preventing you from getting sick in the first place. So static friction, like the preventative medicine to prevent sliding from even happening. But kinetic friction, on the other hand, is like curative medicine. If I get the flu, it's too late to get the flu vaccine, because all the flu vaccine is just the virus particles anyway. I'm sorry, this isn't supposed to be AP biology, right? But instead, I have to go get a treatment for when I'm already sick, like Tamiflu or something like that. So kinetic friction is like curative medicine. We need to cure the problem of sliding. You're sliding, we need to make that quit. On the other hand, static friction, you're not sliding yet, and we need to make you not get started on the sliding, right? That's how I think of the two types of friction. So I use the symbol F with a subscript F for friction. I will not put another letter unless I know what type of friction it is. So if I know that the friction's static, if I know that for sure, I'll put F with a subscript F for friction, S for static. If I know for sure that I'm looking at a kinetic friction, I'll put F with the subscript F for friction and a K for kinetic. But if you're not sure, or if the problem doesn't make a big deal about static versus kinetic friction, just go ahead and call it F with the subscript F, right, for friction, right? So what actually causes friction, just really briefly? So it turns out that when one surface, let's say it's your shoe, the bottom of your shoe, the rubber, comes in contact with another surface, let's just say it's like linoleum floor tile. Okay, so you're in the tile in your lab classroom at your school, right? You've got rubber on the bottom of your shoe. The linoleum's made out of molecules as well. So here's the molecules of your shoe, and here's the molecules of the linoleum floor tile, and they come close to each other. There's some intermolecular bonding that happens. They kind of attract a little bit, okay? So it turns out that when the molecules do not move against each other, have a long time to like bond with each other, right? So it's kind of like if you're at a dinner with somebody with a bunch of other strangers and you're sitting across from the same person all the time, you're going to talk to them, you're going to get to know them, you're going to form like a relationship, okay? Maybe not too serious a one, who knows, right? Okay, but what if instead the molecules are sliding against each other? Well, then they don't have time to form a very good intermolecular bond. Have you ever heard of speed dating? Speed dating is when you do this, where you sit across from a person, you get to know them for a minute, and then either they move or you move, and you're going to get to know a new person. You don't have enough time to really form a bond with that person. So kinetic friction is weak because the molecules don't have time to form those bonds. They're moving past each other, right? Whereas on the other hand, static friction, they're together for a while, so they're going to form some strong bonds. All right, so kinetic friction has an equation. Kinetic friction is equal to mu, which is the coefficient of friction, times the normal force between the object and the surface. No surprise there. The object and the surface have a force called force normal, and the surface exerts another force on the object called friction. So if the normal and the friction both come from the same surface, then they must be related. And then mu with the subscript k, it's called coefficient of kinetic friction. That is a number between 0 and 1 that depends on what the surfaces are made out of. Now, the AP exam has asked tricky questions before where they might say things like, what happens to the coefficient of friction if the object is the same material but is more mass? Okay, don't fall for it. The coefficients of friction only depend on the material, the surfaces, and the objects are made of. Okay, so if you like look up, like stop this video and go Google this list of coefficients of friction, you'll find tables on the internet, but it won't say the coefficient of friction of glass. It'll say glass on steel, plastic on wood, or even different types of wood, balsa wood on pine, things like that, so copper on aluminum. So the two surfaces determine their coefficient of friction, right? Well, what about the surface area? That does not affect the coefficient of friction. Don't fall in that trap. Now, static friction has almost the same equation, except it's not an equation. It's got an alligator symbol. Yeah, I call it an alligator symbol. I know it's a less than or equal sign. It's an alligator symbol, okay? Well, what the heck? It's the same equation, right? It's just got this other symbol called mu subscript s, which is a coefficient of static friction. What's with the alligator symbol? Well, that's what I'm going to talk about with you today. Why is it that static friction is as high as mu force normal, but could be less? And the warm-up was actually had this trap on it. So if you didn't realize on the warm-up that part A had static friction, then you might have fallen into a trap. So remember that static friction is stronger than kinetic friction. So that means for any pair of materials, the mu s will be higher than the mu k, and both of them are less than 1. So between 0 and 1, you have your mu s and your mu k, and your mu s is higher than mu k because static friction is a better, stronger, more loving friction, right? Okay, so here's the deal. If the object's not sliding, then the static friction is going to be just enough to try and prevent any sliding from taking place. That's what the less than or equal to sign is all about. So if I calculate mu force normal for static friction and I get, let's say, 60, well, that's the best static friction can be, 60. But if static friction doesn't have to use his full strength, it's not gonna. Instead, it's gonna use something less, okay? So that's what we're about to see coming up here. So if the applied force is stronger than the static friction's best, then the static friction breaks and the object's gonna start sliding. Static friction didn't win that fight. But if the applied force is less than the maximum static friction, then the static friction is only going to cancel out the applied force, right? So you'll see that coming up here in this diagram. What's going on here? What we've got here is we've got a spring, and that spring is becoming more and more and more elongated. And we know from Hooke's law that the longer a spring is, the more force it exerts. So you'll see that in each frame of the animation, the spring's force just becomes 1 Newton higher, just 1 Newton higher, okay? Now, in this animation, the mu subscript s is 0.6 and the mu subscript k is 0.4, just like in the warm-up. So that was what the warm-up was. And we have a 10 kilogram box and we're using G equals 10, just like in the warm-up. So if I say, what's mu kinetic times force normal? Well, mu kinetic's 0.4, force normal is mg, so that's 10 by 10. So that's a grand total of 40 newtons. So the kinetic friction is 40 newtons, but static friction's best, listen to what I just said, static friction's best, 60 newtons. Now, does that mean that static friction is going to be 60 newtons? Oh, no, sir. Instead, static friction is going to be just enough to cancel out any applied force trying to get the object to slide. So watch what happens here. As the spring exerts more and more force, static friction is just going to be enough to balance the force. See, static friction is not all 60 newtons, but just enough to cancel the spring. Oh, there, whoops. Let me go back. Okay, so what you see is when the applied force reaches 60 newtons, then the static friction breaks. At the moment so here it comes. Oh, and we broke the static friction. And you'll even see up here in the corner that the equation actually changes. So right now we have force friction is less than mu force normal. And if you look really carefully, there's one frame where the static friction is 60 and the spring force is 60, and there's an equal sign for just a quick moment, and then it switches to kinetic friction. So once the applied force becomes greater than 60, static friction is defeated, and in comes kinetic friction. Kinetic friction always does his best. Kinetic friction is always at the maximum. There is no time the kinetic friction is like, I can do as good as 40 newtons, but I'll just do 20 newtons today. No, kinetic friction is always at full strength. But the static friction is like, my best is 60. But if you only apply 20, I'm just going to cancel you out with 20 because I can go as high as 60, but I'm just going to cancel out your 20, my 20. All right, so this is the warm-up. We got the 10 kilogram box, flat surface, mu s is 0.6, mu k is 0.4, right? So part A said, what if we apply 50 newtons? Well, it turns out that, so we got our normal force is 100. So the best static friction can be is 60. We apply 50 newtons, static friction can be as good as 60. So static friction says, well, I'm going to just cancel out your 50. I'm just going to cancel out your 50. So static friction is not going to use its full strength of 60, but just cancel out just 50 of the newtons, right? So you're going to cancel out the 50 newtons that are applied. So that's this moment in the animation right here. That was the moment when the spring force was 50 and the static friction used only 50, not all 60 possible newtons, to balance the force so that no sliding, we're preventing sliding. That's what it takes to prevent sliding from even happening. But now, what if we have 70 newtons we apply? Well, 70 newtons is enough to defeat static friction. So static friction's best is 60. We apply 70 newtons, we break the static friction, those little bonds break, and the box starts sliding. So now we're going to kick out static friction, and we're going to bring on kinetic friction, which is funny when you think about it, because kinetic friction is weaker than static friction, but them's the brakes. Ha 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 ha, brakes use friction. So it's a dad joke. So the forces are no longer balanced. So I have to do Newton's second law. How do you do Newton's second law? The force that helps your acceleration minus the force that's opposed to your acceleration equals ma. It's a force equals ma. No, it's the force that helps acceleration minus the force that is opposed to acceleration equals ma. So the force that's helping acceleration is my applied 70 newtons, but kinetic friction is opposing acceleration with its 40 newtons, the best that kinetic friction can ever do, and kinetic friction always does his best. That's equal to ma, which is 10a. So then I get an acceleration of 3. Okay, that was the answer to part B of our little warm-up, and you can see that here in the animation. That is this frame of the animation where you can see the 70 newtons and the 40 newtons kinetic friction is only going to do his best of 40, not any less, and together they make a net of 30 newtons equals 10 ma, 10a, so that's 3 meters second squared. Yay, look at that up there. Don't you love my little animations? All right, so here's some guided practice. So this is going to be a combination friction problem and kinematics. So we've got the coefficient of friction between the tires and a dry roadway is 0.8. So you got a car that's moving 40 meters per second. That's like 90 miles an hour. So please don't ever drive that fast. On the flat roadway, they're going to brake so hard that their wheels are actually going to lock up and they're going to go into a skid. Okay. Now, of course, in real life, we have all kinds of things in our car to try and prevent that, but this is just high school physics. So we're just going to let it be simple, right? Okay. So initial speed, 40 meters per second. The coefficient of kinetic friction is 0.8. So how far does the car slide before it comes to rest? Got a couple of hints for you. First, use Newton's second law to get the acceleration of the braking car. And then secondly, use a kinematics equation to get the distance. Now, I'm going to warn you, you don't know the mass of the car. Oftentimes in physics, we don't tell you a mass that you think you need. If we don't tell you a mass you think you need, it's going to cancel out. Now, if you can get through A, which I'm going to give you like 3 minutes for, try B. What would the distance be multiplied by if the roadway was wet and we lost half of our friction? Okay, so here's 3 minutes to take a stab at this little problem. On your mark, get set, go. Okay, another programming note. Remember, if you don't like my music, you're always welcome to just hit mute on your computer anytime there's a timer on the screen. Okay, all good. So let's talk about what we're doing here. So the first thing I'm thinking in my mind, the car is going to have a normal and an mg force, and those are the only vertical forces. There's no vertical motion, so force normal is going to equal mg. All right, all good. Let's see. So now what's the only other force? Well, normal and mg cancel, but if I'm driving and I hit the brakes, the friction force is going to be against me. So the only force that doesn't cancel out is friction. So the only force that equals ma is friction. The only force that equals ma is friction. So I'm going to plug in for friction, mu force normal. It's a kinetic friction because I made this guy go into a skid, right? And then force normal is equal to mg. So then friction mu force normal is mu mg. The m's cancel out. So then I just say acceleration is equal to mu g. The mu was 0.8. The g is 10. So my acceleration is going to be 8 meters per second squared. All right. So now that I've got my acceleration of 8 meters per second squared, I need to change an initial velocity, final velocity 0, and an acceleration of 8 into a distance. Initial velocity, final velocity 0. The acceleration's 8. I need a distance. Sounds like a job for v squared equals 2ax. Now, I call v squared equals 2ax the no time equation. I'm going to let you take a guess why I call it the no time equation. But I heard somebody once call it the policeman's equation because it's like that's the equation that policemen use to figure out how fast you're going before the car wreck, right? Like they could figure out, they have a data table of braking accelerations, and they measure your skid marks and things like that to tell if you were speeding before the accident. Was it your fault? So let's just plug into that. So I'm going to plug in my velocity 40 squared equals 2 acceleration times distance, and you get 100 meters, right? So this is kind of, I think we talked about this a couple of lectures ago where we said, oh my gosh, when you're going really fast, you go a long distance while you're braking to a stop. And if there's like a cow or a child in the roadway, I mean, it's not very much time, but it's a long distance. It's an eternity. So don't speed. All right, this whole lecture is actually sponsored by the National Highway Traffic Safety Administration. That's a lie. Don't actually say that to anybody. Okay, now suppose that we have half as much coefficient of friction. Well, if we have, listen to my logic, if we have half as much coefficient of friction, then that's going to cut the acceleration in half because normal and m stay the same. Half the mu k, half the acceleration. Now in this equation, the v is the same. So if A is half, because you have half as much friction, your X is going to double. So now we're talking about 2 football fields that you're stopping. And that's not even counting the amount of time it takes for you to react, to say, oh my gosh, and move your foot from gas to brake. This is when you're actually hitting the brakes, okay? And again, I mean, so let's drive safely, right? We all want to get home safe. Okay, now I want to switch over to talking about forces in 2 dimensions. And so what I've got here is I've got this boy, and he's going to pull his sled, and the sled's got his little sister on it. So let's say the total mass of the sled and the little sister and the flowers is all like 10 kilograms, right? He's going to pull with 100 newtons, and it's going to be angled at 37 degrees. And let me just tell you what I love about 37 degrees. It's that 3-4-5 triangle angle. So just think that your force from the boy is going to make a 3, 4, 5 triangle, right? Now, the kinetic friction with the ground is 0.5. I want you to find the acceleration. So before I start the time here, I'm going to outline some steps here, and I forgot to outline them on my PowerPoint, so I'm just going to do it verbally. So the first thing I would do on your paper, and remember, when you watch these lectures, and I don't care what subject it is, have some pencil and paper ready, right? And remember, if you're watching it live, you can always go back and watch it on the replay. If you're watching on the replay, you can always pause and things like that. So on your paper, let's talk about the sequence of things you should do. 1, let's get a free body diagram on that paper. I'm sure you're already drawing one right now. 2, one of the 4 forces that you drew is a bad force that makes a stupid angle with everything, okay? So let's make that force into components, and let's get a number for each of those components. Then you're going to need to try and get a number for each other force on the diagram. As many of the forces as you can, get a number for them. And once you know all the forces, you can say the force that helps acceleration minus the force against acceleration equals ma, and solve for acceleration. That's Newton's third law. Okay, so I'm just kind of giving you your outline. So here's 3 minutes for your free body diagram for finding all the components and force numbers of Newton's third law, solve for acceleration. On your mark, get set, go. All right, let the time gradually run out here. Hopefully we've got at least some free body diagrams on our papers. All righty then. Okay, so I'm going to have my free body diagram here, and let me just tell you, in a lot of times I have to put my dot for my free body diagram on a grid because that helps me draw longer arrows for stronger forces. So here's free body diagram. Number one, let's just get mg on the page, all right? Just get it on the page. We all know that it's there. It's never going away. It's the elephant in the room, especially if you are an elephant, then you have a huge mg, so it's just going to be there. All right, so let's see. Oh, we got some force tension going on there. Okay, so that's going to be the boy pulling the sled of his with his sister on it. We've got some force normal. Well, wait a minute. Shouldn't the force normal be the same size as the mg? No, this time the force normal is less than the mg because the force normal's got some help from his buddy. He's got force tension helping him out, right? Okay, so you'll notice that the way I drew mg, I drew 5 squares of mg, and when I drew force tension, it was 3 up squares. So I drew force normal as 2 up squares, and that helps me understand how those up forces together equal the down force. I'm going to bust out some friction. I tell my students that they should always draw friction, the arrow, shorter than normal, the arrow for normal. And that's because friction is always weaker than force normal because mu is less than 1. So that's just what I choose to do. Okay, so the normal force is less than mg. The friction force is not mu mg. So you can't just go around saying friction equals mu mg all the time. They're going to hurt you on that, okay? Okay, I'm going to draw an acceleration vector because that helps me. Do not draw the acceleration vector on the dot because it's not a force. So I'm going to draw it out in the boonies somewhere. So there's my acceleration vector out, nearby, so he can help me out, but he doesn't get to actually be with the forces, right? Acceleration is not a force. Okay, so there is any force that's not perpendicular to acceleration and not parallel to acceleration, we need to make into components. So normal and mg are perpendicular to acceleration. I'm fine with that. Friction's parallel to acceleration. That's good. But tension makes this weird angle with acceleration. So I'm going to make tension into components. So weight, normal, and friction are all either parallel, perpendicular to acceleration. Tension is neither parallel nor perpendicular. So we're going to make some components out of force tension. So one of the components is, get this, perpendicular to acceleration. The other component is parallel to acceleration. Here's the theta right here. So I'm going to use the theta and sine and cosine to write some components here. So I've got the adjacent to the theta is hypotenuse cosine. That's ft cosine. The opposite to the theta is ft sine. Okay, all good. This is all numbers I can get right now. I can get the number of newtons for every single one of these little thingies. Okay, so let's so I'm gonna make a couple of equations. So any forces, this is probably all of mechanics hinges on these two bullet points. Any forces perpendicular to acceleration, we're going to balance those forces out. So who's perpendicular to acceleration? mg and force normal and the tension sine theta component. The normal and the tension sine theta component are in the same direction, so they add. The mg is in the opposite direction, so he's on the opposite side of the equal sign. On the other hand, forces parallel to acceleration can't balance because there's an acceleration. That's Newton's second law. So the forces parallel to acceleration are going to net to mass times acceleration. The tension cosine theta helps acceleration, so it is positive. The friction is opposed to acceleration. Opposite direction makes it negative, equals ma. That's how I set up every force problem. Forces perpendicular to acceleration balance each other out. That's the first bullet point. Forces parallel to acceleration make ma. Opposing acceleration makes it negative. And if there's any force that's neither parallel nor perpendicular, it gets componentated, tized. Anyway, okay, so before we solve for the acceleration, let's get we need to get the friction force. And to get the friction force, we need the normal force first. Okay, so I'm going to get the normal force, then the friction force, then the acceleration. Here's the steps. So I'm going to take this equation. Normal, I don't know it. Tension sine theta, I can get it. mg, I pretty much already have it because it's 100 newtons, right? So I've got my normal. The tension was 100. Kid pulls with 100. The sine theta is 0.6. That's the sine of 37, by the way. It's from a 3, 4, 5 triangle, right? mg is 100. Okay, all good. So I've got my normal plus 60 equals 100. So subtract over. And normal is just good old 40 newtons. Okay, all good, all delicious, right? So now I'm like, now that I've got normal, let's get the friction force, right? So I'm going to be all like, okay, so friction is mu force normal. The mu is 0.5. The force normal is 40. So let's turn that into just 20 newtons. So now I know that friction is opposing acceleration with 20 newtons. If I can just figure out how many newtons are helping acceleration, then I can F net equals ma, my way to greatness, right? Okay, so oh my gosh, what happened? Did my slide disappear? What's with the what you need to know? I don't need to know that. Okay. Well, I apologize, folks. Apparently what you need to know decided that you don't need to know the acceleration. I wonder what happened to that. So let me go ahead and tell it to you verbally. So the ft cosine theta is actually 80 newtons. So this is 80 newtons. And the force friction is 20 newtons. So you would write this down. You would say 80 forward newtons minus 20 backwards newtons equals ma, and the m is 10. Now you're gonna have to forgive me. I don't know how to draw on this. I'm using Zoom on mine end, by the way, and I'm not gonna find out in the middle of this. Okay, so we'll figure something out later. Okay, so 80 newtons. Look what I'm pointing to. 80 newtons minus 20 newtons equals m, which is 10 times a. So then 80 minus 20 is 60 net newtons. Equals 10 is the mass times acceleration. So the acceleration would be 6 meters per second squared. Okay, I apologize. I must have, when I pasted this, I might have accidentally overwritten the last slide. So I apologize terribly. Okay, that's actually going to be the last part where I'm going to give you time to talk to each other, not talk to each other. That's my classroom. I'm like, you talk to each other for 3 minutes while I play music and y'all figure out this problem. Nobody's talking to anybody anymore. We're all stuck in our places. Okay, I want to talk really briefly about dealing with friction on an incline, right? So let's just say I had this cart with no friction on an incline. So we know the forces that are acting are good old mg and the force normal. And just in case you cared, normal is actually a math word that is a synonym of the word perpendicular. So we call it force normal because normal is basically a special type of perpendicular, right? So that's why the force normal is perpendicular to the incline. I'm going to draw an acceleration vector. It's going to be off to the side, but it's that way because that's the direction that the cart's going to accelerate. So I'm thinking that force normal is perpendicular to the acceleration. Good. The mg is neither perpendicular nor parallel. Components. We make components out of the force or forces that are neither perpendicular nor parallel to the acceleration. So that's kind of counterintuitive to you. You think that the force normal is the bad angled force, but that's not what acceleration thinks. Acceleration says, ooh, that's at a right angle to me. So the force normal does not affect the acceleration, but the mg is at a weird angle with the acceleration. So we're going to make components out of the weight force. So the normal force is perpendicular. The weight force is neither perpendicular nor parallel. So we draw one dotted line that is perpendicular to acceleration. We draw another dotted line that is parallel to acceleration. Okay, all good. And then let's see. If you look with your eyeballs, I am not going to prove this to you, okay? If you want to do a geometry proof, do it on your own time. It turns out that if you just use your eyeballs, okay, then you can tell that this number of degrees right here is the same as that number of degrees up there. So I'm just going to say that this theta is the same as that theta, and it's called the I can look, you moron theorem, okay? So since the theta is here, the opposite side is going to be the mg sine, because sine is opposite theta. This side is going to be mg cosine theta. A couple of other notes on vector components. The vector itself is the hypotenuse, so the mg is the vector itself, the hypotenuse. The components are perpendicular to each other. They make the legs. Okay, all good. So then, what if I was to write a balanced forces equation? Well, the balanced force equation would say that normal is perpendicular to mg cosine theta. So there you go. No, normal is just mg cosine theta. Okay, that's just equation, no problem, right? But the force is parallel to acceleration, add to ma. It's only one force parallel to acceleration. It's this mg sine theta is helping acceleration. So that mg sine theta is actually what makes you, accelerate downhill when you're on a bicycle or skateboard or whatever, right? I personally call it the downhill force. So if everyone's like, hey, Frensley, how do you calculate the downhill force? I would say just do mg times the sine of the incline angle, right? So we're going to set the mg sine theta equal to ma, and then the acceleration, the mass cancels out. Again, is g sine theta. Now, I know what you're thinking. Wait a minute, Frensley, weren't you supposed to be talking to us about friction? Well, yeah. So now I'm going to talk to you about friction. Okay, but first I want to show you this nifty animation. So you just saw that acceleration equals g sine theta. That means that the acceleration on an incline really only depends on how steep the incline is and the planet you're on. So this red incline is not very steep. So this ball does not have much acceleration. Look at his little speedometer. The needle does not move very much. Low acceleration means that the needle doesn't move very rapidly, but the blue one is steep. So his speedometer goes up very, very rapidly. That's all acceleration really is. Acceleration is just how rapidly does your speedometer needle change, right? Okay, here's an interesting situation. This is an incline that doesn't have the same steepness all the time. So we start with it being really steep, then it becomes less and less and less and less steep. Well, as the incline becomes less and less and less steep, then we have a lot of acceleration because it's very steep, less and less and less and less acceleration. So you see my velocity versus time graph. The velocity versus time graph is very steep at the beginning because we have a very steep slope, but the slope of the velocity graph decreases. The acceleration becomes less as the incline becomes less and less steep. So on an incline, how steep the incline is determines how much acceleration you have if it's frictionless. Now, what if I add friction in? Well, it's really everything we just did. We're going to do exactly what we just did, but with one more arrow on my diagram. Here it is. There's the friction arrow. So Same free body diagram as without friction, but with one more arrow. And in this case, it's not a cart, it's a block. The block is going to slide down the incline, so the friction is going to oppose that motion. The friction is going to oppose that motion, okay? So we still have the same two perpendicular forces. Force normal and mg sine, the cosine theta are still perpendicular. So force normal still equals mg cosine theta. But now when I do F net equals ma with the parallel forces, it would have been mg sine theta equals ma. But with friction, now it's mg sine theta minus friction, minus because friction is opposing acceleration. So mg sine theta minus friction equals ma. Mg sine theta helps acceleration. Force friction is opposed to acceleration, so it gets counted as a negative, equals ma. So what I'm going to do is I'm going to simplify this down as much as I can. I'm going to go ahead and plug in the good old mu force normal. So, and I'm going to plug in the force normal as mg cosine theta. So if friction is mu force normal is mg cosine theta, then friction is mu times force normal, which is mg cosine theta. So now I get this equation. Mg sine theta is the downhill force. Mu mg cosine theta is the entire kinetic friction holding you back, equals ma. And because mass is in every term, and it has to be in every term. If mass is missing from one of your terms, you can't cancel it out anywhere. But because mass is here in this term, and in this term, and in this term, terms are separated by a plus, a minus, or an equal sign, just so you know. Then we can cancel out all the masses. So look, we still have acceleration equals g sine theta, just like before when we didn't have friction. But now we have this term that's going to take away from our acceleration based on how much friction there is. So how can I get a lot of acceleration? I need a lot of sine theta. Sine theta is big when you're close to 90 degrees. So when the incline is steep and close to 90 degrees, you're going to get a lot of acceleration. You're also going to get very little friction holding you back because cosine goes down and is closing in on zero as you reach 90 degrees. So as you go up to 90 degrees, you get more and more and more downhill force helping you go and less and less and less friction holding you back. But if you're really low, like almost 0 degrees, then you've got very little downhill force helping you speed up, and you're going to have a lot of friction force holding you back. And so if your incline is not very steep, it's likely that you'll try to get the object to go and it'll just stop because there's more friction holding it back than mg sine theta downhill force helping it go. So here's my little pictures of sine and cosine, right? So what you see is if you're up near 90 degrees, you've got a lot of positive sine theta and you've got not very much cosine theta holding you back. But if you're down in the low angles, then your cosine theta is holding you back. There's not a lot of sine theta helping you go. So for something that's not very inclined, then the box will not be inclined to go down the incline because the friction is going to hold it back. So as theta increases, less cosine, less friction. As theta increases, more sine, more downhill force. So I have an animation for that. This is a little bit complicated, but if you look carefully, this is a box now and not a little marble, and you'll see the normal force and you'll also see the mg force. So you'll see that the red weight vector is always the same magnitude and always down. You'll also see that there's components. Can you see those components right there? Those are the mg cosine, mg sine theta of the weight force, right? You can also see the friction force becoming stronger and stronger and stronger. Why is the friction force becoming stronger? Because the incline is getting less and less steep. Less steep incline, more friction. Eventually, we get to the point where the friction backwards is balanced and then even better than the mg sine theta helping you go. So the block speeds up when the mg sine theta force is helping it go better than friction's holding it back. But then the speed slows down, the velocity slows down when the friction is the stronger force, stronger than mg sine theta. So about right here is where it seems to change over. So right here, we change from having the mg sine theta force be stronger to friction being stronger. That's when you start slowing down. And in case you care, this specific animation was done with mu equals 1, in case you honestly care, okay, is with mu equals 1. Okay, so what do you need to know? Kinetic friction acts when one object slides against the other. Kinetic friction is always full strength. Static friction can be less than its full strength. Now, static friction's full strength is better than kinetic friction's full strength, but static friction's lazy. He's only going to do just enough to get his job done, right? When you're working in 2 dimensions, your forces and force components that are parallel to acceleration become part of the net force, right? But forces and components that are perpendicular to acceleration are just going to balance each other out. All right, if you have something ready, if you're on a computer, maybe you can push print screen or take a screenshot, or you can just come back to the live view, to the rewatch. If you're doing the rewatch, just push pause right now. Here's some old Physics B exam questions. I told you where you can find them on the internet, and old Physics C mechanics questions, all of which test forces either in 2 dimensions with friction or sometimes maybe even in 1 dimension with friction. I will tell you right now that my personal favorite on this list, if I was only going to give you one to do, I would ask you to do 2015 C mechanics question 1. I think it is the quintessential friction and an incline question. So, but like I said, don't write this down right now. If you're frantically writing down, just go back to the rewatch. It's going to show up in 15 minutes. Or if you're on the rewatch, just push pause, and then you can write down this list and find them. And remember, click on scoring guidelines, and you can see the solution and how points were applied. All right, so that's going to do it for today. We're going to see Ms. Jensfold on Monday. I think she is wrapping up 2-dimensional motion, and then I'm going to be back on Tuesday, and we're going to do drag forces, which is not going to be friendly for P1, but it is going to be friendly for your AB and BC calculus friends. So you might want to invite them to that one too. All right, we're trying to help as many students as we can here. All right, I hope you had a good one. I'll see you next week.